Was that 12 minutes? The other subtitle is here, Fat Chance. Okay. All right, so what I'm going to do today is kind of expand on an earlier model we presented a little some time ago, a couple of years ago, got presented. What we were looking at is a pointer here. Let me just turn that into a, where is that pointer? There it is. All right, we were looking at a discordant anorthosite that's developed in the JM Reef in the Stillwater complex. And along the margin of this discordant anorthosite body is developed a little chromite seam, just like you've seen many times now here, okay? And to make a long story short, what we suggested was that what we are seeing here is that fluids are coming in, they're saturated in plagioclase only, and as they react with a host norite, it picks up, it dissolves out the pyroxene and precipitates chromite at that reaction front. You can kind of think of it as like a roll front uranium deposit, but instead of uranium precipitating at a redox boundary, you can think of chromite precipitating at an orthopyroxene dissolution boundary. And some of the interesting things about this thing is that there's no plagioclase. A lot of plagioclase over here in the anorthosite, a lot of plagioclase over here in the norite. No plagioclase at all in the seam, except for a little bit of rounded plagioclase that's found as inclusions in some of the chromite. And the way that the principle behind this is shown on these two activity diagrams. Activity diagrams, you guys never see much when we're talking about layered intrusions, except perhaps my group. But there's what you would use if you think a fluid is what's driving the mineral assemblage that you have, okay? So here we have basically looking at the magnesium activity versus the silica activity. And in this one here, I show what's happening for the phase diagrams at two different temperatures, one at 750, the other one's at 1050. And what this shows that at point A here, a fluid that's in equilibrium with plagioclase or anorthite, enstatite and diopside, when it is heated up to 1050, it's going to be undersaturated in the pyroxenes and just saturated in plagioclase alone. So therefore, that fluid, if it moves into pyroxene-bearing rocks, wants to react with those minerals, okay? There can be melt around here as well. As a matter of fact, I'll show us that this reaction that we're talking about can actually generate more melt. But the other thing is it does is that when it's reacting with a chrome-bearing pyroxene, is that it locally expands the, increases the chemical potential of chrome, and that expands the chromite field. So it might be here before you start to dissolve chromite, and then it starts to expand, as you see right here. So you can actually go from an anorthosite to a chromite until you get back into a norite over here. Okay. They're late. Okay. All right, so we made a couple of different, at least three different assertions in that earlier paper. One of them is that this same process applies to strata-brown chromite anorthosite layering. We also suggested that these certain redox reactions that occur during chromite precipitation can drive sulfide precipitation, and that furthermore, the addition of chromite can actually be an effective fluxing agent. The first one was actually done for us by a paper by Wolf-Meyer and friends, who suggested that, yes, indeed, still Bushveld anorthosites can be formed by reactive fluid flow, okay? And if you can't trust the organizer of this conference, who can you trust, okay? All right. So rather quickly to go through a couple things that are very important to say about this Bushveld stratigraphy is the orthopyroxene in much of the lower part of this section is actually saturated in chrome. We can't get much more chrome in the pyroxene because the system will start to form chromite as well. And these concentrations about 2 to 3 times that of the pyroxene, the parent liquid. And if you're actually talking about an orthoperoxenite that has several percent chrome in it as well, then those might have 10 or 20% of the chrome content of a parent liquid. The other is that this is a very chlorine-rich part of the section here. And this is suggesting that any fluids around here are going to be very chlorine-rich. And as there's not a lot of good experimental evidence at these temperatures, but what is present suggests that chlorine is important and that chrome is likely dissolved as a divalent chrome-chlorine hydroxyl complex, a neutral one. Okay. And as we also know, did I get too far? No, that's good. The other thing we all know is that chromites like to, sulfide likes to precipitate with that chromite. And we suggested the following reaction sequence. We have the chromite precipitation, which again, this is a divalent chrome. So we need to oxidize it to get it into chromite. So that combines with, say, iron in this case here, and it can get that oxygen from, say, a sulfur dioxide, and that precipitates out a chromite and also forms H2S, okay? So our chrome is oxidized, our sulfur is reduced. If you now have that reduced sulfur, that can be combined also with some iron to precipitate sulfide. So you get a net precipitation reaction of chrome in solution, iron in solution, some sulfur dioxide forms both chromite and sulfide together, okay? And that this precipitation occurs at a 3-to-1 molar ratio. That is, you get chromite with some sulfide in it. You don't get a sulfide-rich layer that has a little bit of chromite in it, okay? And we modeled this as a simple chromatographic system. Okay, we're not going to go through all the details because I don't have time, but basically we looked at whether solution concentrations exceed some solubility constant for various minerals in the system. And we assume that our fluid is going to be saturated just in plagioclase alone, and we let it go into a pyroxene-bearing assemblage here. Okay, I'm going to skip the rest of this part here. And this just shows some of our results here. At 3 different times, we're looking at the mode changes and the solution concentration changes here. Our original system was basically anorite, instantite, and anorthite. It goes off scale here. The original bottom of the system was over here. So at time T1, we've already continued up through the system here. The fluid is moving upward. It's plagioclase saturated only, reacts with the instantite. The instantite, if you will, dissolves incongruently, precipitates chrome and also some sulfide, okay? Because that fluid is not saturated in either sulfide or chrome, that front is going to follow up with that dissolution of enstatite. So over time here, you got a bigger chrome front, more sulfide precipitation, and at this final time here, it looks as you see here. In this case here, for the situation that I'm showing here, the sulfide dissolution front is a little bit slower than the chromite dissolution front, but you can play with this and have it go at any speed you want here. Because you're losing mass from the system, we're shrinking our system down. I assume that this thing is always compacting to leave a fixed porosity, if you will. Okay, so after the time 3, we were down from, started originally at 1 meter, we're down to about just over 80 centimeters or something like that. Okay, now that's what it looks like when it's just moving through anorite. Okay, what happens if you have a, whoops, I must have added something here. Oh, wrong button. Whoops, there it goes. Okay, what happens in the case where we have anorite, but it now intercepts later on, it starts to intercept an orthoperoxenite, okay? So again, this would be the starting system here, anorite down here, an orthoperoxenite up here, then getting back into a anorite up here, okay? Again, it starts out before fluid's infiltrating upward. You're making a chromite precipitating at that front. That continues until it reaches the orthoperoxenite. And at this point here, all it's doing is dissolving pyroxene and precipitating a lot of chromite because you've got more pyroxene, so you have more chrome in the source rock. And if there were already pre-existing chromite, you would get even more. And so because you're now losing basically all this mass of enstatite, it's collapsing down even more, okay? So this system here that we're seeing, an anorthosite, a sulphide-bearing chromitite inside an orthoperoxenite, is sort of a first order Marinsky reef analog here. But wait, there's more. Okay, all right. Order now. And with your order, we will throw in a fluxing effect of chromite, chrome. That is, when you're moving chrome around, if you're moving, I'm going to make it simple and say you're just moving chrome and you want to make chromite, you need to get the other components of chromite from somewhere, okay? Things like aluminum are not particularly soluble. So you have to get that, say, from aluminum, from a plagioclase. And so this is just a very simple melt model. We start with a rock that's basically a norite, mostly orthopyroxene, plagioclase, a little bit of CPX. It's almost solid at this temperature, 1225, 2 kilobars here, okay? What happens if I just add chromite to that system, all right? You precipitate more chromite, but it has to get all those other components for chromite from somewhere, and it gets them by dissolving orthopyroxene and plagioclase. So that it takes out iron, magnesium, and aluminum, but that frees up silica, the sodium that's in the plagioclase, and those are also fluxing agents, okay? So that means that you're making more liquid as you make more and more chromite, okay? The exception is clinopyroxene, which actually increases, and I think that's because you're dissolving the plagioclase, freeing up a lot of CPX, or excuse me, calcium, and that stabilizes the CPX. And I think this can explain some very unusual low temperature CPX megacrystal that we get associated with some chromatites, okay? You can also do it by simply expanding the chromite phase field here. But what this means is, and this is for Marianne, is that the chrome's always growing in a liquid, all right? Even though the rock starts out solid, we're always having some liquid around to make that chromite. Am I almost out of time? Okay, all right. Oops. Okay, so the thing is when this fluid is finished reacting, it just continues in the simple system just to continue moving through the system, okay? But eventually that fluid, you want to know what happens with that fluid. And this is where I get back to a point made by Grant Cawthorne a while ago, that if you actually look at sum up the critical zone, the anorthosites plus the orthoperoxenites actually add up to a norite in the upper critical zone. And so the idea is that we have the fluid that was coming out from this reaction below eventually comes up to where it finds interstitial liquid that is not yet vapor saturated. So it wants to redissolve in there. And this does two things. One is that you're dropping in all the pyroxene components that you leached out from below. The second is that adding vapor actually expands the pyroxene field relative to plagioclase. So you can be making a protolith orthoperoxenite by this process. And to kind of sum it up more and more, so here's down below, we have fluid come up, it's making a chromite by dissolving out the pyroxene. Pyroxene moves up until it sees melt that's not yet vapor saturated. That goes into making an orthoperoxenite. Basically, this rock plus this rock equals our original norite assemblage. And even more complicated, if you want to, you can have later fluids being more water rich, earlier ones more CO2 rich. These leach out the PGE and sulfide that were previously formed and keep moving everything upward. And some conclusions then, chromites can be formed by igneous diagenetic processes in the crystal pile, without the need to call on all these boutique magmas or special conditions that anybody keeps hearing about. It also might, whoops, go back one, can be applied to magnetite anorthosite associations, I think. I leave that for some promising young graduate student to work on. Okay, more specifically, I would like to suggest that this actually applies to trough layers, which are not consistent with density flows, because density flows tend to form flat tops as they fill in channels. They don't form these stacked bowls, if you will. And with that, whoops, went too far.
We are off time, but
Yep.
Maybe one tiny question. One, two.
Can I ask it?
One.
Maybe I can ask it later. So I'm wondering if maybe there's a redox reaction missing. So you, in order to solubilize chromium, it has to be in the divalent state. I think, is that one of the,
Yeah.
so don't you need to reduce chromium